Welcome to AI Explains Everything, where we break down the complexities of artificial intelligence in a way that everyone can understand. Today, we're going to dive into the fascinating world of reinforcement learning, one of the most exciting and rapidly developing areas of AI research. At its core, reinforcement learning is all about teaching machines to make decisions based on experience. Unlike supervised learning, where machines are trained on labeled data, or unsupervised learning, where machines identify patterns and relationships in data without any guidance, reinforcement learning relies on a feedback loop between the machine and its environment. The idea is simple. The machine takes actions in the environment, and the environment provides feedback in the form of rewards or punishments. Over time, the machine learns to take actions that maximize its reward, resulting in more effective decision-making. Let's break down the different components of reinforcement learning in more detail. Environment. The environment in a reinforcement learning problem is the world in which the machine operates. It can be anything from a video game to a financial market, and it provides the context in which the machine takes actions. In a game like chess, for example, the environment is the chessboard, with its pieces and rules of play. In a financial market, the environment is the market itself, with its various assets and trading rules. Actions. Actions are the decisions that the machine makes in response to the environment. In a game like chess, an action might be moving a chess piece to a new location on the board. In a financial market, an action might be buying or selling a particular asset. The actions that the machine can take are defined by a set of rules known as the action space. The action space can be discrete, meaning there are a limited number of possible actions, or continuous, meaning the machine can choose any action within a certain range. Rewards. Rewards are the feedback that the environment provides to the machine in response to its actions. In a game like chess, a reward might be winning the game or capturing an opponent's piece. In a financial market, a reward might be earning a profit on a particular trade. Rewards can be positive or negative, and they are used to guide the machine's decision-making. The goal of the machine is to maximize its cumulative reward over time, which requires making good decisions and avoiding bad ones. Policy. The policy is the set of rules that the machine uses to determine which action to take in response to a given state of the environment. The policy is what drives the machine's decision-making and is the key to maximizing its reward. There are two main types of policies in reinforcement learning: deterministic policies and stochastic policies. A deterministic policy always chooses the same action in response to a given state, while a stochastic policy chooses actions randomly based on a probability distribution. Value function. The value function is a way of measuring the expected reward that the machine will receive by taking a particular action in a particular state. The value function is used to guide the machine's decision-making by providing information about the long-term consequences of its actions. There are two main types of value functions in reinforcement learning: state value functions and action value functions. A state value function measures the expected reward from a given state, regardless of the action taken. An action value function measures the expected reward from a given state and action. Exploration versus exploitation. Exploration and exploitation are two fundamental concepts in reinforcement learning, a branch of artificial intelligence concerned with training algorithms to make optimal decisions in complex environments. In reinforcement learning, an agent learns to take actions in an environment to maximize a reward signal. Exploration involves taking actions to gain new information about the environment. It means trying out new actions that have not been taken before, or that the agent has taken less frequently. Exploration is essential for learning an optimal policy, as it allows the agent to discover which actions lead to the most reward. Exploitation, on the other hand, involves taking actions that the agent already knows to be effective at maximizing rewards. It means using the information that has already been gathered to make the best decision possible. Exploitation is necessary to maximize short-term reward but can lead to suboptimal performance in the long run if the agent fails to explore new possibilities. The exploration-exploitation trade-off is a key challenge in reinforcement learning. To perform well, the agent must balance the need to explore new actions with the need to exploit its current knowledge of the environment. One popular approach to solving the exploration-exploitation trade-off is the epsilon-greedy algorithm. This algorithm selects the best-known action with probability 1 epsilon and a random action with probability epsilon. By setting epsilon to a small value, the algorithm can focus on exploiting its current knowledge of the environment while still occasionally exploring new actions. Another approach is to use upper confidence bound (UCB) algorithms. These algorithms use a confidence interval to determine the uncertainty associated with each action. The algorithm selects the action with the highest upper confidence bound, which balances the desire to exploit known actions with the need to explore new ones. One of the most widely used algorithms for solving the exploration-exploitation trade-off is Monte Carlo tree search, MCTS. MCTS is a simulation-based algorithm that builds a search tree of possible actions and outcomes. By simulating the outcomes of different actions, MCTS can identify which actions are most likely to lead to the desired outcome. MCTS has been used in a variety of applications, including game playing, robotics, and natural language processing. In addition to these algorithmic approaches, there are several other techniques for addressing the exploration-exploitation trade-off. One approach is to use curiosity-driven exploration, which involves rewarding the agent for exploring new parts of the environment, even if the exploration does not lead to an immediate increase in reward. Another approach is to use multi-armed bandit algorithms, which involve testing multiple actions simultaneously and adjusting the probabilities of selecting each action based on their performance. The exploration-exploitation trade-off is a fundamental challenge in reinforcement learning. To maximize performance, agents must balance the need to explore new actions with the need to exploit their current knowledge of the environment. There are several algorithmic approaches and techniques for addressing this trade-off, including epsilon-greedy algorithms, UCB algorithms, Monte Carlo tree search, curiosity-driven exploration, and multi-armed bandit algorithms. Challenges and future directions. While reinforcement learning has shown great promise in a variety of applications, there are still several challenges and limitations that need to be addressed in order to fully realize its potential. One challenge is the problem of generalization, which refers to the ability of the agent to perform well on tasks that are different from the ones it was trained on. Reinforcement learning algorithms typically suffer from poor generalization when the training and test environments are significantly different. Researchers are working on developing algorithms that can generalize more effectively, such as transfer learning and meta-learning. There are also some potential ethical concerns around reinforcement learning, particularly in regards to its applications in robotics and AI. For example, if a robot programmed with reinforcement learning is given a task to complete and receives a reward for completing it, it may learn to complete the task in a way that is harmful to humans or the environment. There is also the risk that reinforcement learning algorithms could perpetuate existing biases and inequalities, particularly if the reward signal is based on data that reflects these biases. To mitigate these risks, researchers and developers are working to develop more ethical approaches to reinforcement learning. One approach is to incorporate ethical principles directly into the reward signal, such as by giving the agent a negative reward for actions that harm humans or the environment. Another approach is to ensure that the data used to train the algorithm is diverse and representative of different groups, in order to reduce the risk of perpetuating biases. Overall, reinforcement learning is an exciting and rapidly advancing field of AI that has the potential to revolutionize many industries and applications. By allowing agents to learn from their environment and improve their actions over time, reinforcement learning can enable more efficient and effective decision-making in complex systems. However, it also has its challenges and limitations, particularly around the issues of exploration versus exploitation and credit assignment. As research in the field continues, it will be important to develop more sophisticated algorithms and approaches to mitigate these challenges and ensure that reinforcement learning is used ethically and responsibly. Reinforcement learning is a powerful approach to teaching machines to make decisions based on experience, using a feedback loop between the machine and its environment. By taking actions and receiving feedback in the form of rewards or punishments, the machine learns to make decisions that maximize its reward, resulting in more effective decision-making. The different components of reinforcement learning, including the environment, actions, rewards, policy, value function, and exploration-exploitation trade-off, work together to help machines learn how to make optimal decisions in complex environments. With the continued development of new algorithms and techniques, reinforcement learning is likely to play an increasingly important role in many fields, from gaming and robotics to finance and healthcare. That's our episode on reinforcement learning. Please be sure to like and subscribe. Leave a comment if there is anything topic you would like us to cover. Thanks for joining us, and we will see you next time on AI Explains Everything.